Howdy guys. So I made the mistake of not recording all the lecture yesterday. So we talked through the labs and how you're going to take the Excel data that's currently up there on Blackboard, and you're going to use that to figure out the velocity relationships for the velocity load, and that'll be from the bench press numbers. And then from the deadlift numbers, that's going to be the power maintenance. And yeah, you're going to have to do a little bit of math, but you can see the load on the bar, and on YouTube you can even see what the sets look like along with the when we're getting the raw data out from the first and the final set. Now, aside from that, we also talked through muscle activation, the action potential. So we're going to start off getting that original action potential going down from the alpha motor neuron to the axon terminal, where it's going to release those vesicles of acetylcholine. Once it releases those vesicles of acetylcholine, they're going to go ahead and go across the neuromuscular junction where the acetylcholine is going to bind to the ligand-gated receptor for acetylcholine, which is going to allow sodium to rush into the cell, which is going to increase the voltage. Once it gets to negative 50 millivolts, it's going to open the voltage-gated channels, which is generating an action potential. So that in turn is going to cause these voltage-gated channels to open as we go down the sarcolemma, eventually down into the T-tubules, and then through the DHB and ryanodine receptors into the sarcoplastic reticulum, where in turn, it's going to cause calcium to be released from calsequestrin due to the change in charge. That calcium is then going to go into the sarcoplasm. That calcium will then bind to troponin, specifically troponin C, which is going to remove or make troponin T move tropomyosin to open up those binding sites on actin, where myosin can then go ahead and grab hold. And then we can start having that power stroke between all the myosin heads on either side. Now, once ATP comes into myosin, it's going to go ahead and release from actin. It will then hydrolyze, which will cock back our myosin, which then it's going to go ahead and grab forward and then power stroke, pulling itself closer to the center. And then that's going to repeat over and over again for as long as calcium is available, along with ATP to allow for relaxation. So hence why calcium is important for muscle contraction. Magnesium is actually another cofactor for the relaxation part, as working synergistically with ATP to get it to release. And then we need ATP to pump that calcium back into the sarcoplastic reticulum. So making sure that you guys remember that, and we can always work through it as many times as you'd like. Then we also started talking about the wonders of thermal regulation and effectively the Katy Perry chapter of how we're going to respond in hot weather, how we're going to respond in cold weather. So the first thing to keep in mind, guys, is it turns out the human body is trying to maintain its temperature within relatively tight confines. We don't want our temperature to go too high. We don't want it to go too low. If it goes too low, we're going to start to shiver. If it goes too high, we're going to sweat. Now, the reason for it is it turns out every cell in your body tends to operate at an optimal temperature. Now, muscle actually operates at a temperature that's higher than your typical resting, but your brain and your internal organs prefer that 98.6 plus or minus a little bit that most of us tend to sit at. So when we're talking about adapting to being in warmer or colder environments, the short-term adaptation is called acclimation. And this is typically taking about 7 to 10 days. A little bit faster or a little bit slower, depending on how big of a difference we're having. Now, acclimatization is we're talking about having lived there for months or years, where you have become far more tolerant of the hot weather or the cold weather. And we also have the conversion. So I gave the story of some swimmers I coached when I was at SLU. We had Marco from Phoenix, Arizona, and then we had Ariel from King Salmon in Alaska. And in November, Marco was wearing double pairs of sweats on upper and lower body and a hat. Meanwhile, Ariel, who had like probably mid-back level length of hair, she would just walk from the pool at 6 o'clock in the morning in St. Louis, which is usually 40, 50 degrees in the morning at that time of year, and just walk to the gym, which was about a good half-mile walk. No issue, because it turns out she was used to very cold temperatures in November. Meanwhile, Marco, he had a rough time that first winter because he wasn't used to it. Now, when we're exercising, most of the energy that we're producing is really being lost as heat. We're only actually harnessing about a quarter of the total amount of energy we're producing to actually get us to do true physical work. And so hence, when we're exercising and in warm environments, we've got twofold reasons of increasing our heat. And the body's trying to have this balance. Heat gain from the metabolic work we're doing, along with the environment around us. Conduction, which is something that we're touching. Convection, which is a gas or fluid going over us. And then radiation, which is heat that's we're radiating out to our environment, or our environment is radiating onto us. So example, the sun on a sunny day. That's where you're going to feel that heat literally just touching your skin. Now, our heat loss is the same basic ways we can gain, except for we have the added advantage of evaporation. And that's literally water evaporating off of us, and that's sweating, which is doing 80% of the heat loss when we're exercising. That's the one that we can really control physiologically. Everything else is a tactical decision. So conduction, once again, guys, that's the heat that's exchanged from touching a surface. So this can be grabbing hold of a hot or cold mug. That is going to be conducting that temperature to your body. Now, convection, this is that breeze going over you on a cold day, which makes it even worse, or makes it even better, because we're constantly radiating heat out into our environment. And so we're constantly slightly increasing the temperature of the air around us. Now, this air around us, in turn, if it's a day where we have a breeze, is constantly being replaced. So we're constantly heating that up. Hence why a breeze feels good on a hot day, but it feels horrible on a cold day. And if it's hot enough, it just feels like you're sticking your head in a blow dryer. Now, once again, the radiation is going to be through infrared rays. And that's where, if you think about the documentary Predator and the thermographic imaging, where you can literally see the amount of energy that that individual is radiating out to its environment. So when we look at all those together of conduction, convection, radiation, those are the ones that we effectively have for dry exchange. And that's going to be, once again, energy that we're both giving off to an environment, and our environment is adding to us. Now, we as humans prefer colder environments because we're constantly radiating heat out to our environments. So if we're 98.6 and we're typically comfortable in 70, 75 degree rooms, and you feel warm in an 80, 85, well, you're actually physically colder, or so you're physically hotter than that temperature. And because, once again, we're constantly trying to release this excess heat. Now, evaporation, once again, is when we're having the phase shift from being a liquid to a gas loses energy, removes energy. And so that's where we're going to get a greater amount of energy exchange when we're exercising, but it can be limited depending on the amount of clothing we're wearing, the thickness of the clothing, and the surface area that it's going to cover on our body. So we have our heat balance, which is if the amount that we're taking in is the same as the amount we're giving off, we're the same. Now, the first one is the metabolic heat, but then from there, when we have radiation, conduction, or conduction and convection, notice how those are plus or minuses. They can be helping us or hindering us depending on the situation. So if all of that is less than zero, we're giving off heat to the environment. If all of that is more than zero, we're going to be gaining heat. Now, what we have is an example of what we're going to see with an individual when they're playing a sport, in that we've got a number of ways that we're gaining that heat and losing that heat. And the key is, like anything else, we want to make sure that we're in balance. Anytime that we're excessively on one side to the other, we're going to have problems. And a key to keep in mind when it comes to acclimatization is the reality that most people are actually not adapted to being out in their environment because they're not outside that much. So you have to be mindful of, yeah, just because it's summer and in theory everyone should be acclimated to being outside, most people spend most of their time in relatively controlled environments, specifically with temperatures within relatively tight ranges, thanks to thermostats, air conditioning, and heating. So we're going to dive further into it, but that's the parts that we went through. Unfortunately, I forgot to hit record appropriately on Wednesday, so hence why I wanted to kind of reiterate a little bit of the things that we talked about, along with touching on how we did talk about the labs. We also went through some scenarios of energy system development, specifically to the parts of the body where it's important in athletes, along with talking about maximal strength and power production and how that's going to be, once again, specific to the task that the athlete is doing. So thanks for listening, guys, and have yourselves a great day. Always feel free to leave a comment if you have any questions. All right, folks, bye-bye.